Oh, I have it. 2.8, inverse and inverse trig functions. I remember being in that picture. Oh, nice. That was my intent. 2.8, inverse and inverse trig functions. How do I look creepy in the picture? I don't know. Was it my facial expression? Oh, wow. Well, I did have Captain Crunch for breakfast. Okay. I was trying to have good posture. 2.8, inverse and inverse trig functions. All right. Have you ever done something you wish you hadn't, Brandon? What if you could undo it, Brandon? Would you? Okay. All right. Yeah. Well, with some functions you can undo what you did. So that's what we're going to be talking about here, inverse function. Remember, two functions are inverses of each other if one of them essentially undoes the work of the other, right? So if you have a little magical function that every time you dropped in a number, it squared it, right? Would you be able to get all your numbers back? Like I drop in a 2 and I get out a 4 and I'm like, oh, woe is me. I want my 2 back. How do you undo squaring that? Square root of it. What's the square root of 4? 2. So I got it back, right? What if I plugged in a 1/2, dropped it in and squared it? Now I get a 1/4. Uh-oh. That was my dad's favorite 1/2. I need to get it back for him. How do I do it? Take the square root of 1/4 and I get 1/2. Okay, now I take my dad's prized number, his -3, and I drop it into the machine, and it gives me what when I square it? A 9. And then I know he's coming home, and I'm like, oops, that was fun. Now I need to get it back. So I take the square root of 9, and I get 3. And I'm like, oh, crap. I can't get back my dad's favorite number is -3. So would you say then that x squared and the square root of x were a nice little pair of inverse functions? Can you get all your numbers back? No, you can't. You can get all your positive numbers back, but you can't get back your negative numbers. So not every function has an inverse function, because to be an inverse, you have to be able to get all the numbers back, positive and negative. And remember what that means then. It means that the two functions have to be 1-to-1. No. So what does it mean to be 1-to-1? Well, we can ask Minnie and Mickey. Okay. To be a function, of course, what does it mean to be a function? Like x squared. It has to pass the what? The vertical forearm test. Okay. And what does that mean? That means that for any x, there's only one y value, right? That means that x is faithful to y. But is that y faithful to x? We'll call it x and x sub 2, x sub 1 and x sub 2. That y is 2 timing the x. This x is faithful to this y, and this x is faithful to that y, but the y is not being faithful. So, in order to be a function, the y's can 2 times the x's, but the x's can't 2 times the y. To be 1-to-1, though, a 1-to-1 function is different. A 1-to-1 function would be something like e to the x or something like that. There's one of your parent functions. Notice that you pick any x, that x is faithful to this y. And notice that y is also faithful to that 1x. That's what makes it 1-to-1. So a 1-to-1 function is, first of all, a function, but it's also, it passes the vertical line test, I should say. But a 1-to-1 function also passes the what line test? Horizontal. So for every x, there's only one y, and for every y, there's only one x. And so that's why Minnie and Mickey are 1-to-1. They are each other's x and y, the only x and y, right? Do y'all know who Goofy's 1-to-1 partner is? Clarabelle the cow. Clarabelle the cow. So you got Goofy the dog, faithful to Clarabelle the cow. Donald and Daisy, excuse me. All right. So the graph of 1-to-1 functions pass the horizontal line test. If a function passes both the vertical and horizontal line test, they're 1-to-1. Okay, so you can code a message and the person on the other side can decode the message, and there's only one way to decode it. All right, so find the inverse functions of each of the following if possible. And that means if it is possible, not if you all have the ability to do it or not. All right, Brandon, you ready? This is one way to represent a function. This would be by listing a set of ordered pairs. And that C, wow, this worked out great. This C should be over here. Okay, a little formatting error. This is the first time for everything. Sweet. Okay, fixed it. All right, so what are we going to, first of all, what are we going to call the inverse function of f? You want to call it g? You can, but maybe there's a name that's a little bit more well suited for knowing it's the inverse, and that's it right there. So we read that as f inverse of x, kind of like f prime. We know it's a function that's related to f, but in this case we know that it's the inverse, not the reciprocal, right? Everyone got that? The reciprocal is not necessarily the inverse, although some reciprocals can be inverses. How do we find inverses? How did you learn back in algebra? Was it 2 maybe? Switch x and y, right? If the function f takes a 2 and turns it into a 5, the inverse function is going to take that 5 and put it right back as a 2. And if the function takes the 3 to a 6, then the inverse takes the 6 back to a 3. This one takes the 2 to a -1. This one takes the 7 to a 4. All right, so I called it f inverse, and now I walk away feeling like I accomplished what I needed to. Is that right? Is that in fact a function? We want to make sure that before we walk away that it is an inverse function. The inverse function has to pass the vertical line test, or the original function has to pass the horizontal line test. How do you do horizontal and vertical line tests on ordered pairs? Any repeat, right? To be a function, you can't have any x's repeating, right? We have 2, 3, -1, and 4, so there's no repeating. To be a 1-to-1 function, though, we also cannot have any repeating y values, do we? 5, 6, 2, 7, those are all different. Okay, so if you have no x values repeating and no y values repeating, it's going to be 1-to-1, and the inverse will be a function. You can also just flip them and then look for repeating x values in the inverse, but it's the same thing, right? Sweet. Letter B. All right, I'm thinking of a number. I'm not going to tell you what it is. Ready? Multiply 5 by my number. What do you get? Now subtract 8 from that number. What do you get? See? And I can tell you exactly now what my original number was. It was 3. That's not a very good magic trick. You have no idea what my number is. No. How about this? Rap, think of a number. Don't tell me. Don't tell me. Now multiply it by 5. Got it? Now subtract 8 from it. All right. Tell me that number. The number that I got. Your final number that you ended up with after you multiplied by 5 and subtracted 8. You got 7. So you started with 3. Yeah. Okay, good. So how did I do that? Is that magic? It's math. It's math, right? Yeah, it's math. Good. All I did to get back this number was I did the inverse operations in the reverse order, right? Right? You told me you got 15, and I knew that you had to subtract. Oh, I got 7. You got 7. Sorry, I'm thinking backwards already. No, you got 7, and I knew you got 7 by subtracting 8 from a number, so I added the 8 right back to get 15. And then I knew you arrived at 15 by multiplying someone by 5, so I divided by 5 and got 3. So what would the inverse be? Can we do it without doing any algebra? I want to get back. So Rap told me his number was 7, so I'm going to call that x, because in general it can be any number. If the last thing you did was subtract 8, the first thing we need to do is what? Add 8, and we're going to get a new number. And then if the first thing he did was multiply by 5, the last thing we need to do is divide the whole thing. Divide the whole thing by 5. And there it is. That's an inverse. Okay? So some of these inverses can be found intuitively. If you want, then you can clean that up to 1/5 x plus 8/5, and it becomes a what? A graph of a what? A line. Yeah. So some of these are intuitive, but let's say that it's a function that's not so intuitively found. How did y'all learn back in the day to find the inverse equation?
Pardon the interruption, teachers. Please turn your TVs to
What'd you say?
4 for the morning announcements.
Switch x and y. Yeah. It's the same thing we did over here. We interchange x and y. I like the word interchange better than switch. We interchange x and y. Now, of course, f of x is just a fancy way to say y. So if we switch them out, we get x equals 5y minus 8, and then all we have to do is resolve for y, yes? Well, when you resolve for y using algebra, you're peeling back the layers, doing the inverse operations in the reverse order. Okay, so if you add 8 to both sides, you get x plus 8 equals 5 times y, and then you divide through by 5, and you get x plus 8/5. And once you do that, of course, you can realize that it's also a line. And, of course, do lines pass the vertical line test? Yes. And so you know the inverse is a function, and now you can give it the inverse function name. How could you tell if the inverse equation was not a function? No, x squared would be okay on the inverse. Yeah, once you have the inverse, before you can call it f inverse, you better make sure that it is a function. The inverse equation will be a function if there's no y's in it that have powers greater than 1, right? Because generally when you have an equation like y squared, that's not a function of x, right? Because there could be 2 y values for every x. So because there's no y squared or y cubed in this equation, we know it's a function. And generally they will be at this level. That's a whole other thing we did in pre-cal. So in other words, don't give it the f inverse function name unless it truly is a function. Now here's one thing to notice about these two functions, and I don't know if it's a coincidence or not, but the slope of our function f is what? I highlighted it for you. 5. And our inverse also ended up being a line, but in its slope was what? 1/5. How are 5 and 1/5 related? They're reciprocals of each other. So we had a pair of inverse functions here. Two functions that were each other's inverse. Which one is the inverse? Is this one the inverse? Or is f the inverse? Well, we started with f, but then we found its inverse is f inverse this. Now, what's the inverse of this function, f inverse? F. So they both end up being inverses, right? They're inverses of each other. If you have a sibling, you don't go home and fight over who the sibling is, right? I'm the sister. No, I'm the sister. But you're a dude. Okay. You win that argument. You are each other's siblings. So anyway, we notice that the slopes of these two inverse functions are what again? One more time? Reciprocals. These inverse functions have reciprocal slopes. I wonder if that's a coincidence. All right, let's look at it probably. Let's look at this. Is this a graph of a function? Does it pass the vertical forearm test? Yes. Is it like Minnie and Mickey? Is it 1-to-1? How can we tell if it's 1-to-1? Does it pass the horizontal line test? It does. So this function will have an inverse. So we learned how to find the inverse of data points, switch the x's and y's. We learned how to find the equation of an inverse, switch x's and y's. How do we find the graph of an inverse? Switch x's and y's. There must be something to that. I wonder if that's a coincidence also. What flavor should we choose for the inverse? Purple? Red. Purple, red. How about just red? Okay. So if the blue graph has an ordered pair at, well, let's see, that would be -5, -3. I'm going to go from left to right. If you switch -5, -3, you get -3, -5. That's going to be right here. And then the point -3, -2 becomes -2, -3. The point -1, 0 becomes 0, -1. The point 1, 1 becomes, when you switch it, 1, 1. Nice. The point 3, 2 becomes the point 2, 3. And the point, boy, I'll call that, how about let's just agree on it, huh? Let's call it 5, 4. And it becomes 4, 5. Yeah. Okay, so all I got to do now is connect those dots. Something like that. And looks like it's doing that. Now, it was helpful to have those points labeled, but you won't always be able to do that. Do you notice any kind of symmetry between the graph of the blue, which is the function, and the inverse, which I'll call f inverse? Any kind of symmetry going on there? Yeah. So this is kind of a nice visual proof, or verification, I should say, that to get the graph of an inverse function, all you have to do is reflect your function you're trying to find the inverse graph of across the line y equals x. Okay? Always. So if you didn't have ordered pairs, you can just draw it and just kind of imagine reflecting it. Now let's come up with some terminology here. The blue graph had a point f of -1 equals 0, right? So the point was -1, 0. Its inverse had a point called 0, -1. Now, are those 2 points the same points on the graph? Are they the same point in the coordinate plane? No, they're 2 different points, but they are kind of related to each other, right? They kind of correspond to each other. One for one function, one for the other. These points here are actually called corresponding points. That's why I use the word. Corresponding points. Good. What would be the corresponding point to the blues -3, 2? To -3. In fact, let's come back over here. The point 2, 5 and the point 5, 2 correspond to each other. 3, 6 is the corresponding point for 6, 3, and vice versa. We call those corresponding points for inverses. Now, why is that important? We'll find out tomorrow. Okay. Make sure that you got the implicit worksheet done. I'm here in the morning, every morning at 7 if you have any questions. No quiz tomorrow. We'll wait till